Okay, let's work through an advanced problem related to projectile motion. There are essentially two types of advanced level problems. One type, the type we're going to work on here, involves a moving target, hitting a moving target, basically. The other type of advanced level projectile motion problem is the type where you're looking to calculate either the initial speed of the launch of the projectile or its initial angle. So let's work through this problem involving a moving target. So here we've got a soccer ball that's been kicked. The ball is initially 35 meters from the goalie, and the goalie, of course, is going to be running in toward the ball to catch it. He's going to catch it with his arms stretched high up in the air when the ball is 2¼ meters above the ground, and we've got the initial speed and angle of the ball's kick. And we need to know what speed, with what average speed, the goalie is going to need to run in toward the ball, toward the kicker, in order to get to the ball when it's at that 2¼ meters above the ground. So I think the first thing we're going to want to determine here is how much time this ball is going to spend in the air by the time it gets to the point where the goalie is going to catch it. And we've got the ball. It's going to be at 2¼ meters above the ground, and of course it's going to be at that height at two different times. It's going to be at that height, say here, when it's on its way up, but then it's going to be at that same height again on its way down, and that's when the goalie is going to be catching it. So we'll see when we calculate the time that we're going to get two times. The shorter of the two times will be the time when it hits that height on the way up, and the second time, the longer time, will be when it hits that height on the way down, and that's the one that we're going to want. So first, like I say, we're going to calculate that time that the ball is going to be in the air, and as we very frequently do in these types of problems, we're going to be using the equation that delta y, the vertical displacement, is equal to 1/2 times the acceleration times the time squared plus the initial vertical component of the velocity times the time. So maybe the first thing really we want to do, which again we often want to do at the beginning of a problem when we have a projectile kicked at an angle, is to calculate what its initial x and y components are. So given that the initial speed of the kick was 15 and it was kicked at a 50-degree angle, we can calculate the initial y component from 15 sine of 50 and the initial x component from 15 cosine of 50. So let's go ahead and calculate that. So I've got the initial y component calculated. The ball is going to start in the upward direction with a velocity of 11.5 meters per second, and at the instant it's kicked, it's going to be moving forward in the horizontal direction with an initial velocity of 9.64 meters per second. Now, in this delta y equation, of course, we need the initial y component, and we do want to know the time at which the ball is going to be 2.25 meters above its initial location, in other words, above the ground. So we'll put positive 2.25, where it's not one of those typical situations where the ball is going to be, like say, kicked off a cliff or something where it's going to be landing lower than it started. Here the ball is going to be caught higher than where it started, so this delta y is positive. Of course, our acceleration, vertical acceleration, is negative 9.8. We're solving for the time with an initial vertical component of the velocity of positive 11.5. So here's where we will rearrange this equation into a standard form and use our quadratic equation solver, either on our calculator or on the web, or if need be, we'll use the quadratic equation. So when we bring that 2.25 over now, that's going to be negative. So my value for C is going to be a negative number, B is going to be a positive number, and A is going to be a negative number. So when I get those two roots calculated, I see that I get, one of the times I get is 0.215 seconds. Of course, that's the time for the ball to hit that height on the way up. So that's why that's the shorter of the two times, and this is the time I really need. This is the time it's going to take for the ball to, go up to its highest point, start coming back down, and get back down to the point where it's 2¼ meters above the ground. So that's my time of the flight, at least up until the point where the goalie is going to catch it. Next thing I want to determine is how far out the ball will be, horizontally how far out the ball will be at the time that it's caught. So there I'm going to use my equation for the projectile's motion in the horizontal direction, using that horizontal component of its velocity, which we know is not going to change, and this time that we just calculated, the time it's going to take to get up to the 2.25 meters on the way down. So we'll go ahead and calculate that. That'll tell us how far out horizontally the ball has traveled. Works out to 20.5 meters. So that's how far out the ball is going to go. And we need to realize, though, that the goalie is 35 meters out. So he's going to need to run in to catch this ball, and he's going to need to run in a distance of 35 minus 20.5. That distance works out to be 14.5 meters. So that's how far the goalie is going to need to travel. And assuming that the goalie starts running at the instant that the ball is kicked, the speed that the goalie is going to need to have, and we're assuming he's running with basically a constant speed, but we're looking for what average constant speed he would need to run at. We would take the distance that he needs to run, which is the 14.5 meters, and divide that by the time that he has to run that distance in, because he's going to be running only during the time that the ball is actually in flight. So we'll take that 14.5 meters and divide by the 2.13 seconds, and that will give us his speed. Okay, so calculating that, we find that his average speed as he runs toward the ball, catches it 2¼ meters above the ground, he would have to run toward the ball, toward the kicker, toward the ball at 6.81 meters per second. So that's going to be his constant speed.